Hello, good day. I hope you are well today. My college, Alexis Ricardo Noriega, and I, your server, Erwin Casiel Peña Cardona, we talk more about translation matrix so that you can have a better understanding of them. Next, I will talk about matrices, what they are sort of used for, among other things. Well, the first of all, what in an array? Uh, a matrix is a square or rectangular table of dot coded elements. Uh, Arranged in rows and columns, where our row is each of the horizontal lines in the matrix and a column is each of the vertical lines. As shown in the following image, you can see different types of matrices, each one which has a different function. These matrices in this case are those of rotation. In this case, these matrices help to use or rotation of a robot in the axis of rotation, x, y, and z coordinates. And what are they used for? Uh, Matrices are generally used to describe systems of linear equations, systems of differential equations, or to represent a linear map given a basis. Matrices are described in the field of matrix theory. Uh, these have a wide range applications. They serve of use for too many things, but in this case, we will focus more on kinematics. Now we will talk of translation matrix. First of all, let's understand what is translation. Translation implies in movement of an object, person's position or event. The translations of an object, for example, refers to the transport of a thing from one place to another. The transfer of a position, for example, means a change of position in the field of work, but in this case, we speak of the translations of coordinate axes in x, y, and z. Now, if we can explain what is relationship is, mm, these are of type translations that occurs when a figure is moving from one location to another on the coordinated plane without changing its size, shape, or orientation. It it is a translations matrix. Addition can be used to find the coordinates of the translated figure. In science, translations is a particular case of affine transformation, but not a linear transformation. Homogeneous coordinates are generally used to represent the translation by a matrix, and thus being able to express it as a linear transformation over a higher dimensional space.
Okay, so to understand how we get the translation matrix, we need to understand what is the translation. So when we analyze an object, we understand by the most primitive way that every single point of one object analyzed is moved and the exact same distances between each point is the same except with a different reference mark. So, what is translation? As we can see, the new point is moved by the same distance it already had, but adding the differential of each axis. So, we have that in a mathematical way that x1 is equal to the x plus its differential. In the same way, we have y1 is equal to y plus the differential of y. To put in this in a more simple way on a matrix, we have an identity matrix, and in which we put that the identity matrix is when we have no rotation, we have the differential of movement, this being in this form because when we multiply by the same point, we end up with the point we already had plus the differential of each point. Knowing this understanding, we can decide scaling this up to 3 dimension. We have the exact same identity matrix having the differential of each point multiplied by the raw value of each point that we are analyzing, having as a result the each point adding up to the differential of the new point. So, knowing that the translation function we can understand by the more raw or primitive way, that ignoring the rotation part of a matrix, we know that the first part, the corner up left, is a rotation matrix. Down left, we have a matrix of zeros because we don't really use that yet. Up left, we have the displacement value that is one column by 3 rows, and a one because we have to maintain the form without rupturing the multiplication and application. So we have the translation on x, having A as an x translation, B as a y translation, and C as a z translation. Knowing this, we can go up to a primitive way. No, we can go to analyze what is translation plus a rotation, knowing this an homogeneous matrix. So we have our first reference coordinates, and we have to rotate on z, we have to translate on x, and we have to translate an L value. So this will give us a new system of coordinates. Having this as a result, we have a z translation matrix in which we have our angles of each angle that we are rotating. We have the displacement on L and multiplied by the angle that we are working on. Having thus this displacement or new system of coordinates that we will be working on. Knowing this, we have that in a three-dimensional way. When we translate one point having the L part having a differential, we have a new system of coordinates.
Mm, to complete more this part, I will think about matrix, homogeneous matrix, which goes hand in hand with the translation matrix. Uh, what is an homogeneous matrix? The homogeneous matrix is an 4 per 4 matrix that translates a vector expressed in homogeneous coordinates from one coordinate system to another coordinate system. What is a homogeneous matrix good for? Homogeneous transformation matrix are used to represent the position and orientation of a rotate and translated system with respect to fixed system. Transforms a vector expression in mobile coordinates and its representation in a fixed system. Rotate and translate a vector with respect to a fixed system. Uh, Taking into account below to explain exercise with which you will be able to understand what a translation matrix is and see how of the matrix is solved. And first of all, the problems tells use that we have a translation in the x and y axis with the leg of 7 and angle to 80. And it also doesn't say that it has no rotation. Why does it not have rotation? As shown in the matrix, L is the axis staged wherein it is, as you can see. To understand it a little better, it says that the first row is for the x, the second is for the y's, and the third is for the and z's. And as we can see, they all stay in the same same place. That's why it's said to have no rotation. Once identified, we proceed to extract story is going to be translated in X and Y, and how to do that. And good way to obtain X is to multiply the length, which is the can use will be the hypotenuse, which is the equation is equal to 7 multiplied by the cosine of the angle, which is 80. This as a result will given us what is accelerated in x. For y is exactly the same, but to change the constant by the sen, multiply the length, which is this case, will be hypotenuse, which equal to 7 multiplied by the sen of the angle, which is the 80, and this as result will give us what is translated in say. Uh, in this way, we obtain the resulting matrix, which tells us that in hand no rotation and that it moved at x 1 point to 115 and at y point 80 193. Uh,
Okay, now moving on to an example, we will know that we have our non-rotational matrix and we have a displacement. Knowing this, we have that our route point is at 2, 3, and 2. So that will be our point 1. Our point 1 is ubicated at a space at XO, YO, and ZO. But we are having a displacement, a translation. So this gives us our new point. What will this mean? Okay, grabbing the displacement, the translation matrix, we know that our new coordinate will be ubicated at this point in space, marked as red. So our new point will be added up to the point we already had plus the differential that the new system of coordinates gave us.
So The manipulation of parts requires the spatial movement of its end. It is necessary to know its position and orientation with respect to the robot base. It is important to define the reference coordinate system located at the base of the robot and its associated x, y, z axis, forming the O x, y, z system. Rotation matrices can be defined on spaces of any dimension algebraically. The position in a plane is defined as the positioning by 2 degrees of freedom through 2 independent components. The position in space is defined as the positioning by 3 degrees of freedom through 3 different components. So, there are different coordinate systems to position a point. These are Cartesian, polar, cylindrical, and spherical, and we can represent like this. However, if what we are going to describe are rotations in a three-dimensional coordinate system, then a single 2x2 matrix is not enough for us. We need a 3x3 matrix, which will be the angle theta will be different in each matrix, and we have the rotation matrix by x, the rotation matrix by y, and the rotation matrix by z, the representation. So, in three dimensions, 3 different rotations can be made. Rotation in x-axis, rotation in y-axis, and rotation in z-axis. And we can help us with the law of the right hand. A position is unambiguously established by a position vector Pm with 3 components with respect to a reference system called M, with origin that of this reference system and endpoint the position. The components of the vector Pm are the projections of each of the axes of the reference system M, and we represent the point Pm with the
Well, I am going to present the rotation matrix, but viewed from the analysis point. As my partner Edwin said, it is important to know how the analyses are in the 3x, because since we are going to working with a robot, it is important to know how the rotations are in this same axis, because we are working with robots and we have to know the movement that the robots have. Now, how are we going to obtain this rotation analysis? We can do an analysis and projections, the vectors or the plane. In this case, we have the original plane that its vectors are x, y, and z. And the unit plane that its vectors are u, v, and w. To know how these axes are projected, we can do it with a product, which is the projection, the one with respect to the another one. In this case, we obtain an scalar matrix. The analysis. For example, how is the dot product? The dot product is the multiplying 2 vectors. In this case, the first vector is 3 rows by 1 column, and its components are x, y, and z. And the second one is the dot product of the unit vector that it composed by 1 row and 3 columns, and its vectors are u, v, and w. As I mentioned before, we can get a scalar matrix or generic matrix. In this matrix, it refers to the rotation that have the three axes, but in the next line I am going to explain better. The general matrix. The result of a dot product is a matrix, a general matrix 2, 3 by 3. In this case, I am going to explain how is the component of this matrix. In the first line, in the first row, we can observe the vector u and its projections of the axis x, y, is z. This projection mentions how is the behavior in this axis. In the second line has the first one. We have the vector v and its projections in the axis x, y, and z. Finally, we have the w vector and its behavior or its projection in the axis x, y, and z. If we want, we can decompose the general matrix and it can be the rotation by each one x. In this case, we are going to present the x rotations. Following the formula of the general matrix, we can observe how is the behavior of the vector u respect to the axes x, y, and z. As we can observe, the vector u and the projection of the axis x, one is above the another one. In this case, the representation mentioned that the number is 1 because it's in the same way. And as we are going to working with the unitary vector, also is the magnitude of the vector is 1. For the projection of the vector u respectively the axis y and z, it refers to the we have an angle of 90 degrees and the representation of this is 0 because we don't, it's mentioned that we don't have a complement or projection in this axis. For the second line, is in the first line the vector v respect the axis x mentioned the same way that we have the angle of 90 degrees and in this case no have projection or complement. In the second line, the projection of the vector v respect the axis y mentioned that is a cosine because there is an angle in this part and the function, the trigonometrical function that we use for this rectangle triangle is a cosine. By the representation of the vector v respectively the axis z, mentioned that is a sine. In this case is the another trigonometrical function. In the projection of vector w of the axis x, it shows that has an angle of 90 degrees. So in this case, we don't have projection or component. And the projection in the axis y, if we lengthen the negative part, it shows that is in negative. The vector is in the negative part. So in this case is the less, the sign less. And the trigonometrical function is the sine. Finally, we have the projection in the axis c, and in this case has the another ones. If we review the part of the angle or trigonometrical function that we are going to use is the cosine. The rotation y, we have the same analysis and we make the matrix of rot y, that is cosine of theta 0, sin of theta 0, 1, 0, la sine de theta 0 and cosine de theta. And the C rotation, we have the same analysis as the another ones, and we mentioned that is this rotation get it. Because the sino de theta, la sino de theta and cosino de theta.
Rotation matrix example. The rotation matrices that we use are those of x, y, and zeta. Before starting, we must know that a rotation matrix helps us to know in which coordinates a point will remain after making a rotation. Then, an example of its application will be the following statement. Perform rotation of the z-axis of 90 degrees for the point P. 2 in x, 2 in y, and 2 in z. Okay. First, we need to identify the matrix we will be working. In this case, it is the matrix of zeta. Then, we substitute the theta for the values of our angle rotation and calculate the values. Those are the values of this matrix. And finally, we multiply the resulting matrix with the matrix of the point P. So that is the way we have the coordinates of point 1 according to the main axis. And here we can see how the rotation diagram behaves and how the point moves. The black plane is the original plane, while the red one is the plane already rotated 90 degrees. For the location of the point P, to the coordinates are those 2 in x, 1 and 2, 2 in y, 1 and 2, and 2 in z, 1 and 2. For the point 1, this we use these coordinates less 2, 1 and 2, and 2 in y, 1 and 2, and 2 in z, 1 and 2. Okay. The following examples are very similar than the others. The first step is the same, to identify the matrix that we need to use. After this, we substitute the value of theta, calculate the matrix resulting, and multiply for the point P. And those are the new coordinates for the point number 1, this one. And it's the same. In the plane original, located the first point, 1, 2, and 3, 1, 1, 2, and 1, 2, and 3. And we have the point. And for the point 1, use these coordinates. 1 less 0.7, like in here, and 3.5. 1, 2, 3, and 0.5, and we have the point. Or if you want, you can use these coordinates to locate this point, but you need to use the plane in color red. For example, 1, and after this 1 and 2, and 3 in Z. 1, 2, and 3. And it's the same. We have the point. And for the rotation of Y, it's the same process. The first step is identify the matrix, in this case rotation by Y, and substitute the values of theta and calculate the matrix resulting. Multiply by the point, and we have the point and locate it in the plane. And that's all for me. Thank you for your time.